It's a great pleasure for me to host Professor Debnarayan Jana from the Physics Department of Calcutta University in Geetham Physics Department for a invited lecture here. So the institution building is shown here, where I also studied, and I was taught by this young fellow standing over here. And I think many of us, including Sudeshna, was also taught by him in our postgraduate days. And since then I passed out in 2008, and this is almost 13 years. I've been in touch with him over the emails and phones, and eventually when I came to know that he's traveling to Bangalore for some personal reason, I tried to grab him and requested him, which he kindly agreed to come and meet us here in the physics department. We are extremely delighted to host him, and Professor Jana will be talking about 100 years of Bose-Einstein statistics, and the stage is all yours. Thank you very much.
Okay, thank you for inviting me to this Geetham University. Although I think I was a virtual speaker about the Google Meet in a couple of years back, and but this is completely different reasons which I shortly requested him that whether I can be able to at least meet the young faculty members and the other students who are actually doing very good research. And I'm really very honored to see that these people are actually doing very frontier research areas with their stipulated fund and their extreme academic duties. I really appreciate that one. And I can tell you that I've been there in Srinagar and other kind of private universities. Forget about in the other eastern part of these things, but this kind of universities actually is one of the very rare kind of universities which I have visited in last couple of years, with so many faculty members. Maximum of these faculty members are 7 to 8, but at least 15 faculty members are doing in different branches of physics and concentrating both on the different logistic problems of their own, and also collaborating with abroad as well as our national laboratories. So I'm really very happy, and I hope that in near future this will be one of the cornerstone in Bangalore city, although it is a little bit outskirts, I guess. But hope I will also try to send some good students if we found out suitable and interested to work it here. So I'm really very much happy to see all these things. So with this background, today's talk will be very pedagogical and some not very kind of deep heuristic way of looking this Bose-Einstein statistics. Mainly I will try to glimpse some of these history of science and what prompted Bose to take up this work and try to gather with that thing. So I will try to finish with this the scheduled time, and this is the kind of a Nature article which tries to remind us that Bose statistics was developed by Bose in Dhaka 1924, and this was the article to remind people this is the 100 years, that is 2024. So this is a very nice way to present that Bose reached a century. And as you know that Bose was very good at mathematics, which further used to teach in a different way of mathematics. So let me start with a very simple mathematics which he used to do in secondary arena. So let me start with this one simple mathematics. So take off a 3-digit number, reverse it, take a subtractions, and then you again reverse the result and add it off. So you might get two kind of options with that thing. That this subtraction can give you either 3-digit number or a 2-digit number. So if you get a 2-digit number, then you multiply by 2, and then you get a 3-digit number. Again you reverse it and add it up. The question mark gives you, if you do it in your own hand, by every people, whatever you can think it, you will get a common universal answer. Question is, why do we get a common universal answer? What is the background of this thing? You will get, you will try it later, you can get 1089. That's the answer, everyone will get it. Now you can ask the same thing, that is it possible to get a unique answer for 4-digit number? I will say at the end of this thing that it will be different. Why is it different? I will give some simple argument to that. So with that thing, let me start with these two pictures. That was the earlier days when he was a boy, and this is at the after the VC of Viswabharati at the last stage. So February 4, 1974, he actually expired. Okay? And if you go to his home in the North Calcutta, this was the original Bose's house, and now it is actually little bit taken up, decorated by the government to have a heritage house, and this house looks like this with a nameplate given to it, National Professor Satyendra Bose. And if you see the galaxy of these his colleagues and teachers and friends, you can easily find it out. The Satyendra Bose is here, then that is our is there in that building, and this in between there is PC Rai, Acharya Prabhu Chandra. So that's wonderful picture of all these things, and all of them are very great, rather than in different branches of science. So it was really he got very much pioneering that basically the renaissance of the science. And this is one of the famous mark sheet he obtained. You will be find to interested that both Meghnad Saha and they were the classmates, and they actually graduated not in physics but in applied mathematics, and this is the first time they have got joined first. Meghnad Saha also got the same mark, total marks, but the numbers are little bit different. His marks are quite appreciating. This 100, only lowest mark is 84. And this is still a record in Calcutta University. No one has still crossed that thing. Only 2 people came very close to that thing. One was famous, the director of SN Bose, Professor C.K. Majumdar, Chanchal Kumar Majumdar. He was 8 marks away from this marks. And another fellow who was there in these coming years, he is now faculty in Germany. He was 15 marks away from this thing. And she was about to cross it, but we pulled her a little bit back. Less marks in practicals. She got 50 in my electrodynamics paper. She got our solid-state physics 50 marks. So we cannot make in any less marks than 50. So only we can really give less marks in practical. Out of 50, 41, 42. So sometimes she was very bothered, said, what happened to practical here? Then I showed this mark sheet. So would you like to cross that man? So no, okay, fine. Okay, so this way we can just stop her, otherwise she could really cross that thing. And this is the book which actually was written by both Meghnad Saha and Satyendra Bose. This book is written as a solid special theory of relativity. Remember, that time there is no kind of textbook available for relativity. They translated completely from German language, read those paper by Einstein's paper himself, then translated and taught in the class. Amazing. And if you look out, that time we have collaborated the number of questions and the moderated question, the standard is quite good. We are still far away from that thing. And the questions were moderated by no other than Santa Chandra Maulanavis. And that time, the question paper setter and the moderators' names were there in the question paper itself. So students can know that who are my paper setters, who have moderated. Nowadays it is not possible because of different restrictions. But I can just tell a story behind it, that the questions were set that time 4 or 5 years within physical review papers. Can't you imagine? Now we cannot teach all the papers to the students. And the questions were 16 marks each. So you have to answer 6 questions out of 10, 16 into 6, 96. 4 marks were given for excellent answers. So look at this thing, that the way they used to teach it. And this is another very famous picture. The between Jagdish Chandra Bose is there, Satyen Bose is there, and Meghnad just beside it. Okay, so this is also one of the famous picture. All of them, like D.M. Bose, Gyan Chandra Bose, these are very famous people in physics and mathematics. And this is very well-known picture at the time of Dhaka University when he formulated this Bose-Einstein statistics. Remember, most of us forgot that people try to tell that he did the work from Calcutta University. It's wrong. Actually, the work was done when he was at Dhaka University, Bangladesh. Okay, that time it was not Bangladesh. This was completely India. Okay, so this is the actually picture in the University of Dhaka, 1921. Okay, and the recommendation for his readership job was given none other than Einstein. So I just want to read the last two lines of this thing. He has also at his command an extensive knowledge and certain ability in our science. As university teacher, he will certainly develop a successful and prosperous activity. He did not have a formal PhD degree. Remember, this is the only person in India who was awarded professorship and other national and FRS without having any PhD degree. Formally, M.N. Saha did a paper in PhD paper, but he did not do it. So, to readership, only an external person who can actually recommend freely, and he didn't ask Einstein to give the recommendation. Somebody requested Einstein, can you write down a letter for Satyendranath Bose? This is the letter, you can see it. Okay. So this is the situation. He was also a superintendent of a hostel and in Dhaka University, and that time there was influx of many students. Teachers used to flock together, and he has a own way of testing the students and testing the faculty member. I just came across one incident from Dhaka University professor who said that he has a very nice book on mathematics that is called arithmetic. So in arithmetic, when we studied in our childhood days, we used to solve the problem by the help of algebra. Putting, let it be x, formulated an algebraic equation, solve it. So we have solved the arithmetic problem by algebraic method. He did not allow that algebra to be used here. So he used to give a very good problems to all of the students and ask them, please make a solution within 7 days. So he has categorically divided. Within that way, one person, Qazi Mahadur Hossain, something like that, I remember, that he did it excellent, and then he took him to Prashanta Chandra Maulanavis to make him prepare for that time the most wanted branches of science, statistics. And rather he did it excellent in statistics. And he used to recommend Prashanta Chandra Maulanavis, say that he is like my brother is. Tell him to teach such a way that he could be a statistician like you. So he used to give a sabbatical leave there. He was their head of the department, so that that person could come to eyesight and learn for 1.5 years, then again go back. So this way, actually, Bangladesh learned statistics from our that person. Okay, and I think this is a very famous picture. Can anyone identify the tall man on the left hand side? Yeah. Who is the second woman in the middle? Can you name that person? No. This is a famous person. The first female PhD from Calcutta University and from the Asia. This is Purnima Singh. She did it work in X-ray of clay, soil. And the paper was published in Nature. Can you think of? And his actually daughter, Suparna Sinha, was my supervisor's wife, Joseph Samuel from Bangalore, Raman Research Institute. So he's still there as a emeritus professor. And so you have seen Satyam, this is the rare occasion Satyam Bose has wearing a trouser. You have never seen this thing. And the person came in Howrah, he took them to Sipur Botanical Garden and then brought them to our Calcutta University, the same room where I am sitting now. So amazing. There are lots of photographs. I am not sharing that one. But one thing I should tell them, that he was driving in a car that time. So Dirac's wife was wondering that how many students can accommodate in this car, because all of his students were there with him. Then Dirac made a comment, Bose-Einstein condensation, so any particle can be accommodated. If you see in the kind of van or something in a nearby village, you will find out how many people, sometimes I cannot count the number of heads one can handle together. But this is one of the rarest occasions that Dirac made a comment on that thing. And he was not only a physicist but also a very good musician. Dependrayan Jana, so was his good friend, and that day actually he took them to Dependrayan house, and he also played Ezraz, and Dependrayan also have a music with both Dirac and Dirac's wife. And it will be really amazing to know that that time Summerfield also came there, Lewis de Broglie came there, Niels Bohr also came to the same department. Summerfield came to check whether C.V. Raman has done the experiment correctly or not. He was visiting Japan, then Lord Rayleigh asked, because C.V. Raman himself wrote a letter saying that I should get the Nobel Prize because the paper was published in Indian Journal of Physics. Then he wrote it to the telegram to Nature to publish it immediately. And he criticized already in a newspaper that I will get the Nobel Prize within a year or so. So that was on the 28th February, that's why National Science Day. And he got the award later on. So before this announcement was there, he took already ship voyage already there. So people already, actually the support was directly from Lord Rayleigh. And Lord Rayleigh actually sent Summerfield to check, and Summerfield was quite happy to see that experiment, and he was convinced that this should be done. So these two people supported completely so that he could get the Nobel Prize. Okay, so I will not go to this thing. Now I will enter this the topic of Bose-Einstein statistics, forgettable reminiscence, and the stories and all around. So we will start with the black body radiations. This is basically a electromagnetic spectrum having the highest wavelength to the lower wavelength. You know this thing very much, so I don't want to do that explicitly. But one thing is common to them: all of these electromagnetic waves travel in free space with the speed of light. Everyone has different frequency, different penetrating power, and different wavelength. Okay. This is also a famous picture of this Bose-Einstein. So I will not go to this thing. What he used to do in science college, these are the couple of papers. The first one about the Saha-Bose equation of state, published in Philosophical magazine, and the other two was also on Philosophical magazine on the quantum theory of spectral emission, Rydberg's law, and in the bulletin of the Calcutta Mathematical Society. These are all the continuum mechanics, this stress equation of equilibrium. So these are the paper, and he used to teach the general modern physics and the general laboratory in our science college. So let's start with this Planck's black body radiations. He was trying to connect this Lord Rayleigh's the two law, Rayleigh-Jeans law, and the lower and higher wavelength, and also the peak connecting the displacement law, that is lambda maximum into T must be constant, right? Now the question is that how to connect these two different wavelengths. So that was some kind of proposition. The main problem was there, we have to have a quantum theory of oscillators, but how these oscillators are distributed over the energy level. That is mean counting of states. So counting of states has that problem. See, he actually gave a kind of, by somehow who can put cloud, that the spectrum can be fitted by equation. So the factor 2 into 4 pi square p square dp, p is h nu by c. So this factor was giving a problem to be understood. By that time, by the way, these two people, the Professor Meghnad Sahu was teaching at thermal radiations in Allahabad University, and Professor Bose was teaching the same topic in Dhaka University. So Professor Bose invited Meghnad Sahu to examine externally to some of these practical students. So on the discussion, he told what you are teaching there. So he told that, can you figure it out the physical meaning of this phase-space factor? He said, I have also a confusion. So he brought some Pauli's recent papers and other calculations. He said, why don't you think it? So it was actually Meghnad who put an impetus to Satyam Bose to rethink mathematically. So Meghnad Sahu has a very good belief on the mathematical ability because he was a partner of this thing. He knows that thing, what he can do it. Because Meghnad Sahu also tried that thing, but he could not do that problem. So Meghnad Sahu has said this thing in one of his biography, that I could not do that thing. So this is the factor I was telling you, h pi hc factor. So most of the times given a kind of a connecting law, but how do you count these states? That was the problem. So people tried it, but you cannot get it immediately. So that was done by counting of states. What we know in statistical mechanics, indistinguishable identical and distinguishable identical. So in the left hand side, I have taken 3 particles in 3 different energy levels. These are distinguishable particles, and I have arranged in many ways, right? That is classical distribution. But if you are indistinguishable, so you cannot distinguish the white with the black one, so the number of states is like this thing. And this is basically the so-called Bose-Einstein distributions. So once you have that thing, you can now calculate the number of ways you can do that thing, and the statistical mechanics tells you the entropy has to be extremized, that is S equal to KBL and W, and you reach at the equilibrium, calculate the what is the equilibrium under the condition, total number of particles is conserved, total energy is conserved. That's the way we do the statistical mechanics. So he exactly has done. This is the Bose's research paper in his own handwriting, and you can see the this is from the Dhaka University library. So this proved conclusively the work was done from Dhaka University. Okay, and this is the way actually we also teach the BSc students the preliminary things. And the most important part is that we have shown the distribution and counting of the states. The one thing is very important, the photon number is not conserved. That brings out the very essential meaning of chemical potential. What do you mean by chemical potential? Chemical potential in energy, if you add one particle to n particle system or take out one of the particles, so the energy difference is given by the chemical potential. So mu equal to minus del E by del N, or in terms of the statistical ways, you can also define in terms of the free energy. So in case of if there is no conservation of photon number, we can make this chemical potential to be 0. So what is the full game of this thing, which have been written by 1, 2, 3, that he was the first person to tell that photon had a spin 1. And Einstein by that time was not very much convinced. He said, why photon? It is a 2 direction of polarization. When Planck also told it's a 2 is polarizations. But he was the first, and it was C.V. Raman who first also agreed in a paper in Indian Journal of Physics that Professor Bose has really shown us that photon spin is 1. So these are the two confronted. Nowadays, this can be confronted by exactly light matter interactions. When you have a electric dipole tension, the angular momentum must conserve with the plus minus 1 electric. So that conserves that it has to be photon spin with 1. And by the way, photon is a transverse character, so divergence B is 0. So that's why we call it two directional horizon. But this should be called it spin. Actually, Einstein was not convinced it, and this is the way he actually calculated. 4 pi t square dp is given by this, and then this 2 factor is coming from the spin. Okay, and this is the letter he wrote to Einstein, because this paper was originally submitted to Philosophical magazine, but it was rejected. Then he sent to Albert Einstein and introduced himself that you may not forget the name, that these are the two persons in Calcutta who translated and read your papers in Germany language and translated to English about the special theory of relativity. So that's why he introduced himself. And this is again the same thing, but I just want to share you with the Einstein note here. I think that's the important thing. In my opinion, Bose's derivation of the Planck formula signifies an important development. The method considered here is also the quantum theory of ideal gases, which I shall discuss elsewhere. I think this last line is the crux of this thing. Professor Bose did not envisage the condensation of Bose particles. I think if you could tell that thing, there is a material particles which can condense at low temperature, just utter the word, because the number of particles at low temperature can agglomerate in a huge number that can change the macroscopic property. Quantum mechanical wave functions become macroscopic quantity, which is observable quantity. It's a collective excitation of these quantum particles. I think presumably his name could have been considered as a Nobel Prize winner. Here he is the genius who can easily translate, because he was bothered about reconstructions of Planck's black body radiations by a different counting of states. It's a good basic research, no doubt about it. But he did not mention, when he was returning back, rejected, he could rethink the problem. Can I apply these statistics to some experimental object for this thing? Here lies the beauty of Einstein. He could immediately show for helium-4 gases there is a possibility of Bose-Einstein condensation and superfluidity. And that actually gave a big breakthrough in the experimental quantum spectroscopy. Okay, so I will not go to this thing spin story. So the formal derivations what we do in our MSc classes is through partition function and the distributing to all particles, assuming they are distinguishable. In each of these cases, the total number of particles is constant, total energy is constant, and you will get this Z as like this. This is the usual, we can get it in a canonical distribution functions. But for a photons, they are identical and number of photons is not conserved. So you can see that the second step, N1, N2, each independently can take this from 0 to infinity, because there is no restrictions on the number of particles for each energy levels. And as a result, we get this the Bose-Einstein distribution 1 by e to the power beta epsilon s minus 1. So what I was telling, why he could not see that the denominator e to the power beta epsilon s at epsilon s goes to 0, it could give a 0 value such a way that ns could actually diverge. That was the beauty which Einstein pointed out. Now what we have learned from this thing, you can see that thing, the thing which have been written in here actually can be given a particle and wave, and we have learned that Bose and Einstein, which we have got it like this way, and that describe these particles with integer spins are called bosons. These name bosons were coined by none other than Paul Dirac in his book Principles of Quantum Mechanics. He classified the two sets of our objects, subatomic particles, fermions and bosons. So he actually coined the name bosons. Okay. So these are the simple things which we do in our class. If two fermions in a box is there, the wave functions must change sign if you exchange the number of particles, and we have shown this thing, and this way if two bosons are there, the wave functions will remain symmetric if you change this x1 to x2, and we know that this Pauli's exclusion must be obeyed by the fermions, so that if the two particles lie at the same position, there is no wave function, so no two quantum particle can have the same set of four quantum numbers, only they can differ if their spins are up and down, so they eventually satisfy the Pauli's exclusion principle. So what are the quantum statistics? We have the two sets of quantum statistics, one obeys by the spin half integers, odd number of spins, that is the Fermi-Dirac statistics, and another is the Bose-Einstein statistics. Now if you arrange in a harmonic oscillator type of potentials, integer spins such as photons and rubidium atoms, which were used as a Bose-Einstein condensations later on after 71 years after 1924. So 1995 it was discovered, and 2001 I think they have got the Nobel Prize for this thing. So if you have a spin half integer particles like electrons, protons and neutrons, because of this Pauli's exclusion principle, this is the way we can arrange it. And the distributions of Bose-Einstein at different temperature will look like this thing. However, the Fermi-Dirac distributions will look like this thing. Sorry, this should cut at the same point. I did a mistake there. And this should be symmetric about 0.5 actually. So that is a mistake. And if you look out, these three statistics will merge together at reasonably high enough temperature and low density, such that this thermal de Broglie wavelength n lambda cube condition is satisfied, and we can think three different statistics at a low enough temperature. So low enough temperature, Bose-Einstein condensate will take place for Bose-Einstein particles obeying B statistics, and the remarkable properties of these electrons will also be signified at low enough temperature. So all these statistics will merge to Maxwell-Boltzmann statistics at the high enough temperature. So as I have told you, Bose-Einstein condensation is the extreme aggregate of the system of particles. They are all in the same state, and you can have a macroscopic descriptions of this thing. You can designate by the number density. So wave functions have their macroscopic property, not the individual wave function is important. So you can have a kind of Pitavesky gross equations. It's a Schrodinger type of nonlinear equation which can be solved to do that thing, time dependent Schrodinger equations, and you can see the condensation will take place at a low temperatures and combine this as a macroscopic object. And one can think of that this probability density is everywhere same. So one wave function for the whole system, that's the macroscopic quantity of that thing. And as I have told you, theoretically predicted by Satyanarayana Bose and Albert Einstein 1924, then first practical relation by these three people, Cornell, Quetelet and Wimmel at 1995, almost 71 years. People can wonder why so much time was required. One way of answering that, how to observe low temperature, because the temperature required to see this thing is nanokelvin, 159 nanokelvin, that is 159 into 10 to the power minus 9 K. So normal way of attaining such a low, that is still far away from our zero temperature, right? So that's the lowest temperature we have achieved so far. And you have to measure also in a different way. That's a more technical part. I don't want to go to that one. So as I have told you, 2001, these three scientists actually got the Nobel Prize. So what is ultra cold? So I have told you that this how this higher phase space density will occur, which actually is a function of temperature. So the phase space at low temperature becomes very dense actually. So if you look out the typical ultra cold, this is the scale, We have room temperature 293 K, Antarctica is 200 K, dilution refrigerant 2 millikelvin, and ultra cold is this region. So that's the nanokelvin. So that's why it took so much time to observe this Bose-Einstein condensation. So I'm not going to the much more theoretical things. I'm just coming to almost end. These ultra cold atoms actually are the techniques that took so much time, and you'll be happy to know that Prof also sometimes back has thought about that thing. So he has wrote a letter to the physics. Today I have seen that he was thinking, but not done enough way that how to observe that thing. So laser cooling, Doppler cooling, magneto-optical trap, this is sometimes called MOT. So these are the way one can actually achieve this Bose-Einstein condensation. Then there is called a evaporative cooling, micromagnetic traps, and evaporation. Like here we have shown a schematic picture that when you actually drink a coffee, you can think of that what is the temperature you can do it. So evaporation of 2% T molecules produces a 20% change in temperature. And this was a paper by Hess in Physical Review B. He calculated that thing with a cup of tea. So evaporative cooling also of these rubidium atoms actually give rise to this thing. We have to be spin separated, there is magnetic trapping, and then we can have a typical Bose-Einstein condensation. So condensation always occurs when a critical density is reached. There is trapping and chilling of bosons. Of course, the wavelength of the wave packages becomes quite big enough so that can be talk about a overlapping or a condensed situation, and we can have a laser cooling until 100 microkelvin. But as I have told you, we have to go below that temperature, that is in the nano range. So like adiabatic demagnetization, that is millikelvin, microkelvin, that is not enough to do that. You have to go below. So temperature is always measure of the kinetic thing, half mv square equal to 3 by 2 kT. So you have to make this velocity to be smaller enough. So you can think of those who are actually higher velocity, you can throw away from your distribution. So if you throw away, the tail will come and the temperature will come down. This is a very simpler way of understanding that one, because whatever temperature we is basically measure of velocity, right? Square of measure of velocity by the equipartition principle. So this is the way actually done by this laser cooling method, and this is lots of I think technological genius. That's why it took so much time, and there are many effects can be shown. One is superfluidity and superconductivity, because in the superconductivity Cooper pairs also can be thought of going through a Bose-Einstein condensation. But remember, Cooper pairs are approximately behaving as a bosons. They have in-between characteristic features, and we can actually try to understand the collective phenomena in solid state physics by understanding these three important phenomena. There are many interesting coherence effects. I have not listed enough, but one can think of, and these are all over macroscopic quantities. So BEC was found in alkali metals like rubidium, sodium. There is some interesting aspect because they are bosons, and each atom is a small magnetic compass. They are also less interacting. They are also have a small repulsions, because otherwise they will not go to the low enough temperatures. Okay. So as I have already told you, these are the two main branches people are trying to work on: BEC, BCS crossover, and coherence. These are the main things which have come out of this study of Bose-Einstein condensation. So I am almost through of this thing. So this is almost the last slide of this thing. This 57 rubidium atoms. These are kind of some typical number of atoms per unit and temperature, and how does this thing happen. So this has to there. I'm just skipping these two. This is the brief summary. 1924, S.N. Bose described the statistics for identical bosons. 1925, Albert Einstein first predicted the occurrence of BEC over the particles where condenses. and 95 kernel women and Ketterle observed Bose-Einstein condensation in 2 atoms, 87 rubidium and 23 sodium. And last year actually Ketterle came to Bose Center. There was a conference in October, and this is an interesting scale Landau used to play himself. This is a logarithmic scale of our scientist. So he put Newton, that is log 1 is 0, Einstein is 0.5, but 1 there is the only name Bose. Bohr, Heisenberg, Dirac, Bose, Wigner, Schrödinger. And Landau himself put to scale 2. Okay. So people sometimes ask that why he did not get the Nobel Prize, that I don't want to go now. There are some articles I have written long back about Bose-Einstein condensation. I don't want to go to this thing. I will just go to the last thing about the problems. He also spent couple of times to conduct Bangio Vigyan Porishad. Still now they are publishing articles for the young children or the population of science articles. So I also invite you to participate in some way to that thing, those who are can at least write it. And I guess one person from RRI, Professor Raman actually he used to write few articles, and I think only science magazine which is still now available in our West Bengal. There is no issue which has not been published, which has not been coming through that thing. There is no issue, no kind of article which have been missed by any publications, disaster or not. Till date, I think people are still reading this article. So that was his whole aim to understand science to the common people by mother tongue. Okay. So this is the actually the solution of the mathematical quiz which I gave you in the beginning of that thing. You can play around that thing. This is my own way of understanding. There is another simpler way of understanding this thing which was done by another professor from Jadavpur University, I think, who are there. He could easily recognize Professor Dhiranjan Rai. So he has written a book, I just checked it, Entertainments with Mathematics. He gave a very nice way of arranging that you will get this number 1089 immediately. And as I have told you in the 4-digit number, why you don't get this number? Because there is B and C, there are 3 situations. B greater than C, B less than C, and B equals to C. So if you do this algebra, you will find out B greater than C, there is a universal number 1089, which was there in the 3rd digit case. There is an extra zeros. And B less than C, there is a unique number of 4 nines. And B equal to C, another unique number 10989. So if you are interested in lots of other kind of puzzling and mathematics, this person has delightedly established simple. This is for the young children who wants to culture the mathematics knowledge. So these are my group of students who are working with me for PhD. The person Dept Mondal, he has joined IIT Mumbai as a postdoc this month only, and the other people are trying to complete it as soon as possible. So thank you for your kind attention. I think I have hopefully finished before the time so that the students can go. And if you have any questions or comments, we'll be happy to share. Thank you again.
So this Bose-Einstein condensation, do we in India we have some institution where it can be seen?
Yeah, that's a very good question. Actually, in my PhD days, people hired people in ISC Bangalore, but it was not done properly. Even in RRI, Himaram Chandran, another group of people were there, but they are not able to see it. There are other places in TIFR also, they are almost close to it but could not see it. In our Calcutta University, Professor P.N. Ghosh group also, only in one day they see it for a momentarily, the peak of this density. So the question is why? Because our stability of low temperature, that's the biggest problem.
But in the category group,
They could. Because the atoms has to be prepared properly, the laser strength and the measurement. Unless you reach that, I told you 1 to 100 microkelvin, you will not be able to see it. You have to reach 159 nanokelvin, 159 into 10 to the minus 9. Unless you reach that temperature, you will not be able to see the peak of this thing.
But that requires human intelligence or resources?
Resources. Because you have to separate. See that thing, laser cooling is there, magnetic trapping is there, some of this spin flipping is there, so you have to separate that thing. You have to have a less number of atoms and they will also have less repulsion, all these factors. So technique is also there. So this is a new way of designing temperature because it was not earlier there. So that was the technique. So that's why as I told you, Astronomin around 1976-79, he made a comment that adiabatic demagnetization or the formal low temperature is not enough to observe Bose-Einstein condensation. So he was working on the hydrogen, not sodium, not rubidium. But he made a remark. I have seen that Physics Today article. So lots of people are trying to.
So we gave up or we still doing it?
No, he gave up. He gave up.
So I'm saying, as in, we gave up that we will never.
No, he said that he mentioned negative that this the formal technique of achieving low temperature is not possible. That's the comment he made it. Then people tried to do that. How way we can go to lower temperature? That's the problem. I think Bangalore has a good project, but they have not been able to succeed. They have got a good guy from that group also, and do that.
So Raman group did not make Bose-Einstein. I thought they were successful for some.
No, they didn't get it, but she actually expired due to cancer and other things. Actually, that time I was there. When she got that project and other thing, she was from BRC, and then she joined as a faculty in RRI. And Professor Andal is also there. They actually tried to. Andal has a experience in Finland with a group of people, but they are not able to see Bose-Einstein. But the one thing is good there, they could build up a quantum optics group and a nonlinear optics group. That way, subsequently, they have succeeded to do that thing. But not the whole project was focused on Bose-Einstein condensation. That was not there. But people have done theoretical calculations from India, Bose-Einstein condensation, like using Gross-Pitavesky, like JKB also has done some calculation, Gross-Pitavesky. Raka Dasgupta, I think you might see, is now a faculty. She also did some calculations. So theoretical calculations were there.
N. Kumar also.
N. Kumar, I was about to tell you, yes. He was that time our director. Okay, at least I will ask Simonto, I will send one actually film. I didn't go through that because of so many things. So you can show to the faculty member the Quantum Indians. This is a film by Raja Chaudhary. If somebody has seen it, very good. This is about the three.
It's in YouTube.
Yes. So if somebody, some students have not yet seen it, I least ask them to at least see it, or at least download and see it. The three scientists, Meghnad Shah, C.V. Raman, and our Satyendra Bose. This is a brief life history and few comments. It's a documentary film, so you can see that. That will be very nice.